In the name of Almighty God, I'm Master Sankosh, and today I want to talk about pressure acoustics. The pressure acoustics branch has interfaces where the sound field is described by the pressure P. The physics interface solves acoustic problems in the frequency domain using the pressure acoustics frequency domain interface, where the Helmholtz equation is solved. Transit systems are modeled using the pressure acoustics transit interface, where the classical wave equation is solved. Nonlinear effect can be included here using the nonlinear acoustic Westervelt feature. The boundary mode acoustics interface is used to study propagating modes in the waveguides and ducts at a given frequency. Only a finite set of wave shapes can propagate over a long distance. To efficiently solve the radiation and scattering problems, the pressure acoustics boundary element interface solves the Helmholtz equation using the boundary element method. The interface is fully multiphysics enabled and coupled seamlessly with the finite element based interfaces, both acoustic and structural. The pressure acoustics time explicit interface uses the time explicit method based on the discontinuous Galerkin finite elements to efficiently solve large transient problems. This physics interface can also be solved on a GPU. It can also be coupled to the elastic waves time explicit interface. Force domains can be modeled in a time domain with this interface. Finally, two interfaces exist to model high frequency acoustics. The pressure acoustics asymptotic scattering interface for scattering problems, and pressure acoustics Kirchhoff-Helmholtz interface for radiation problems. A large variety of boundary conditions are available, including sound hard walls and conditions for applying sources. There are radiation symmetry, periodic, and port conditions for modeling open boundaries. Impedance conditions include models for different parts of the human ear, human skin, simple RCL circuit models, and more frequency-dependent impedance conditions in the time domain can be set up using the built-in rational fitting approach. The physics interface also have several fluid models which in a homogenized way mimic the behavior of sound propagation in more complex media. This includes the propagation in porous or fibrous material, the pro-acoustic and anisotropic acoustic domain features the propagation in narrow structures of constant cross-section, the narrow region acoustics domain feature and fluid models for defining bulk absorption behavior. Monopole, dipole, and quadrupole point sources can also be applied. So-called perfectly matched layers (PMLs) are also available to truncate and unbounded computational domain in both time and frequency domain. Finally, the exterior field calculation feature can be used to determine the pure pressure in any point outside the computational domain. Dedicated results and analysis capabilities exist for visualizing the radiation pattern of the exterior field, near and far field in polar two-dimensional and three-dimensional plots. For example, we are talking about acoustic pressure, which can transient some, for example, microfluids or something in a big net, for example, specifically where we are talking in a symmetry and perfect layers, perfectly matched layers, specifically for the big networks, for example, Cassandra. And for example, we can assume if something disappear in a city, it can appear another city and again go to the another perfect layer to another city. So elastic waves, the elastic waves branch includes physics interfaces and multiphysics interfaces for modeling the propagation of linear elastic waves in solids, porous materials, and piezoelectric materials if necessary. The interfaces are readily coupled to fluid domains using the built-in multiphysics couplings. The physics interfaces on this branch are the solid mechanics, elastic waves. For modeling elastic waves in solids, the port boundary condition is specifically implemented to model and handle various propagating modes in elastic waveguide structures. For elastic waves, for precisely modeling the propagation of sound in porous material, isotropic or anisotropic, it includes the two-way coupling between the deformation of the solid porous matrix and the pressure waves in the saturating fluid. The physics interface solves Biot's equation in frequency domain using a UP formulation. It includes two formulations for the loose mechanisms. The Biot viscous losses for modeling rocks and soils, and the Biot Allard or Biot GCA that includes thermal and viscous losses for sound absorbing material in air. Elastic waves are time explicit for modeling the propagation of linear elastic waves in solid using the discontinuous Galerkin time explicit formulation. The interface is suited for modeling large problems with a memory efficient method. Piezoelectric waves time explicit and multiphysics interface for modeling linear elastic waves in piezoelectric matters using the discontinuous Galerkin time explicit formulation. The interface is suited for modeling large problems with a memory efficient method. Now I want to go to the acoustic structure interaction. The acoustic structure interaction branch has interfaces that apply to phenomena where the fluid pressure causes a load on the solid domain and the structural acceleration affects the fluid domain across the fluid solid boundary. The physics interface under this branch are the acoustic solid interaction frequency domain and acoustic solid interaction transient multiphysics interfaces. Acoustic shell interaction frequency domain and acoustic shell interaction transient multiphysics interfaces. Acoustic piezoelectric interaction frequency domain and acoustic piezoelectric interaction transient multiphysics interface with support solving and modeling the electric field and the piezoelectric material. The piezoelectric coupling can be set can be in a stress charge of strain charge for acoustic solid poroelastic waves interaction and acoustic poroelastic waves interaction multiphysics interfaces. Acoustic solid interaction time explicit multiphysics interfaces. The multiphysics interfaces consist of two or more single physics interfaces. For example, pressure acoustics, frequency domain, and solid mechanics together with a multiphysics coupling. Here, the acoustic structure boundary coupling many more couplings are supported. For example, coupling pressure acoustic to membrane or multi-body dynamic interfaces. So thank you so much for watching my tutorial video until the end. Today is 25th of May 2026. Time is 10:18 a.m. And also you can download the proper and appropriate uh, file, a simulation file from github.com/masterscript from Tehran City.